Hello everybody. Let us start our discussion today. We now consider the universe as a whole. The journey to observe the universe as a whole started with a set of observations done by Edwin Hubble at the beginning of 1900s. So what was Hubble doing? So he was certainly doing observations and or interpreting observational data. So what are those observational data? So let me write down the observational data first, what they were observing first, because that's how you understand things. So they measured distances to nearby nebulae, and so they called them nebulae because they did not actually know what they are. But so was the first person to point out that there are actually galaxies like our galaxy outside. So let me write just galaxies here. So they used the method of Cepheid variables to measure these distances. I think this was discussed in the last lecture, the introductory lecture. So it's a class of distance measurement is called luminosity distance measurement, which we'll come back to later in a later class. What is meant by luminosity distance? But the other thing they could measure, so they measured redshift. To the nearby galaxies, the same galaxies they were observing. Okay, so let me tell you, let me show you one and try to make you understand one of the modern day measurements of the redshift to the galaxies. The luminosity distance measurement we have already talked about. What is luminosity distance? How it is related to things that we'll discuss today will be talked about in a later class. So what you see here is the spectra of one of the nearby galaxies. The galaxy position is written over there, and so some certain other numbers written which is not of importance for us. This is measured by the SDSS, Slow and Digital Sky Survey. Uh, this is a part of that measurements. So what have they done? They look at the spectra of the galaxy, and when they look at the spectra of the galaxy, they see these spectral lines. So first of all, a galaxy spectra is nowhere near to a black body spectra like for the stars, but it has a continuum which you see here. So that's a continuum, and on top of that you have these spectral lines. So the lines that you see with lines, those are marked by those vertical lines. So these are there. So then what do? You note down the wavelength which is in the x-axis for all of these lines. So the wavelengths you note down for all of these lines. So wherever you have a line, you note down the wavelengths, and then you ask the question that what are these spectral lines? Where are they coming from? Like for example, if I look at say this particular line, which transition, spectral electronic transition is causing this line? Like for example, we talked about the hyperfine structure transition in hydrogen atom. That was an atomic line, but most of the lines that we know of happens because of transition between two electronic levels. So what are those? And that they have identified and marked here. So each line they know exactly where are they coming from. So what are the original spectral line. Now how to do that is a little complicated, so I will not go into that. But what happens, I can show you. What happens is the following. So this is a depiction of the spectra of a galaxy, and you see that they have purposefully written in given it in different colors, and you see there is some striking similarity between these spectra. So every time you see these, you observe that there is a shift in the spectra, right? So this line, for example, has moved there and then there and then there and then there. This line, for example, has moved there and then there and then there and then there. And you can see the amount of shift is different at different uh, places. The shift is more here compared to the shift here. But at least if I know that what are those lines, so all of these lines, if I can identify, I'm just pointing them out in the lowermost spectra, then I will be able to find out, if I look at this spectra, then I will be able to figure out that what are those lines in the red spectra, or vice versa. If I look at the red spectra and I know about the blue spectra, then I will be figure out where are these lines in the red, what are the lines in the red spectra from my knowledge in the blue spectra. And that is the idea, that once you know that, you realize the following. You realize that the lines, or Hubble realized that the lines are all redshifted. What do I mean by redshift? I mean, if I consider that the lines are observed at a wavelength of lambda observed, and the original wavelength of the line when it was emitted is lambda emitted, then the lambda observed is more than lambda emitted, and the redshift is defined this way. So that's the definition of the redshift. And it's called redshift because if the observed wavelength is more than the emission wavelength, then Z is greater than 0. Okay. So that's what they observed. That's what Hubble observed. But that's not all the observations. Now, Hubble is looking at the galaxies at different redshift. When he saw that these galaxies are redshifted, the spectra from the galaxies are redshifted, he tried to figure out why this can be. And one reason for redshift, he thought, so Hubble thought, reason for redshift is that the galaxies are moving away from us. Okay, so if you think of that reason, so then so the galaxies you can think of are moving away from us with a velocity v, and this velocity divided by the speed of light he interpreted as redshift. So if I know what is my redshift, I can get this velocity, just multiply z with c. Okay. So remember, now with this interpretation, he had two measured quantities. So he had two measured quantities. The velocity and the distance, right? So he plotted velocity versus distance, and this is his original plot. So in the x-axis, the plot is not very, the resolution of the plot is not very good, but you can see distance over here, and you can see velocity over here. These are in kilometer units, and these are in parsecs unit. So there is 10 to the 6 parsecs. So these are basically megaparsec units. So it's 0 megaparsec, 1 megaparsec. He could go up to 2 megaparsec. And you can see, if you don't draw these lines, they are kind of scatter plots. But Hubble drew this line, and he found out that the velocities are proportional to the distance. And he figured out the proportionality constant just by fitting this straight line. And I don't know whether he called it, but we call it Hubble's constant. So we write V equals Hubble constant times T. So this is the distance that was measured. The distance is the direct measured quantity, remember? And this axis is the velocity. The velocity is inferred. So the velocity is inferred as c times z. And when you plot it for all these nebulae, so these dot circles and the points are all nebulae, don't try to ask the question at this level, what are these circles and what are these field circles and open circles, why there are two lines, etc. This plot has historical importance, but the present day the plot will look quite different. But anyway, so when we plotted the distance versus the inferred velocity, he found that the velocity is proportional to distance, and the proportionality constant we call Hubble's law. So this is V equals h naught d. So let me write down what they are. So V is coming directly from here. D is measured by luminosity distance. H naught we call Hubble's constant. Okay, roughly there are very precise values of Hubble constant as measured today, but roughly the value is 70 kilometer per second per megaparsec. And you can see immediately from Hubble's plot why is this peculiar unit, because velocity is measured in kilometer per second and d is measured in megaparsec. So h naught has a unit of kilometer per second per megaparsec. Okay, so that's Hubble's observation. And remember that the fact that the distance is proportional to velocity actually comes from the fact that the distance is proportional to the redshift. The proportionality from the direct observation, the proportionality is actually redshift versus distance. This is the actual measured proportionality, which Hubble interpreted as velocity and distance. Okay, so let us go back to what Hubble observed once more. So they measured the distance to the nearby galaxies, and they measured the redshift to the same galaxies. The redshift is defined as the shift in the spectral line observed minus emitted wavelengths divided by the emitted wavelength. So this is a dimensionless quantity. Redshift is a dimensionless quantity. And Hubble thought that the reason for the redshift is that the galaxies are moving away from us. So he equated redshift with V by C. So V came out to be C times Z. And when he plotted this V with the luminosity distance, he got this relation. So let me keep this relation in a little better form, because this is what is the crux of the story so far. So the relation is V equals h naught times b. And the actual relation, if you remember, as we said, is z is proportional to d, just because v is the inferred velocity using this formula. Okay, so what we will try to do next is try to understand where this proportionality comes from. Is it really that the galaxies are moving away from us, so that is the reason for this proportionality, or there is some more uh, interesting reason for this proportionality? So it turns out that it is not that the galaxies are moving away from us. The actual reason is more interesting, and that is what we are going to learn today. Now, if we try to use the general relativity that we know to model the universe itself, what is the basic assumptions that you will need? Just like we saw for the Schwarzschild metric case, here also we will start with an identity, with a symmetry, and the symmetry being the fact that the universe is spatially homogeneous and isotropic. If we take that assumptions, we can uh, we can actually simplify the Einstein equation a lot. And this assumption is named as a principle. It's called the cosmological principle. And this is only spatial homogeneity and isotropy. Homogeneity was not there in Schwarzschild metric. Here we have homogeneity and isotropy both. And you may imagine that there can be vacuum solution for the universe also, but that will come back to later. But usually the universe is not considered as completely empty. Just such empty solution was devised by Einstein and de Sitter, but that is not what is considered in modern cosmology. So in this spatial dimension, the universe has essentially the maximal symmetry. Once you assume this, then the metric become a lot simpler, and this metric goes by the name of Friedman, Robertson, Walker, and Lemaitre. So it's called the Flrw metric, and I will write the line element for this as always, because that is what we will be using mostly. But I mean, one can write line element or the metric. You will know one if you know the other. So this is c square dt square. There is a function which is a square t, and then I should write L square here. I will come back to what it is, and then there is this term dr square by 1 minus kr square, and r square, the line element on the surface of a sphere, d omega square. D omega we have also used in the last time. I'm not going to write it explicitly again. So let me tell you what are these different things. This takes the dimension of the length, and the coordinate r here is dimensionless because all the length dimension is there in L. This at is called a scale factor. This is the only undetermined function of time that remains in this metric. Everything else, all the other functions are determined. And this k is having the information of the spatial curvature. K equals to 0 is flat, is 1 is called a closed, and -1 is called open. So these are the only three values possible for K. And this is your FLRW line element. What we will do is, we will consider the case for the flat metric. The universe is known to be spatially flat so far. This is an observational fact. And as I said, so far, I mean, if you observe with more precision, you may see that it has changed. So I can set k equals to 0. What I have written down here is a solution that comes purely from mathematics, assuming that the spatial part has the maximal symmetry. Now I have used an observational fact to set k equals to 0. Then you can just set L equals to 1 and give the dimension of the length to the coordinate r itself. So the flat spatially, the flat FLRW metric will look like the following, with which we'll be working on. And you can see immediately why AT is called a scale factor, because what it does is it changes the measured distance between 2 points by itself, by the factor of itself. So that's what it is called a scale factor. And we will see that to explain Hubble's observation in this theory, it plays a major role. You see, so far we have not used general relativity at all. General relativity is there in that equation, in that Einstein equation, which we have not used at all. We have to still use Einstein equation to figure out what is A as a function of t, but it's remarkable that with these symmetries and consideration that the spatially flat, the only undetermined quantity now is the how the scale factor varies as a function of time. If it does not, if it's just a constant, then you go back to the Minkowski spacetime. Okay, so now let us try to explain Hubble's observation using this metric. So Hubble's observation is all about the path of radial light rays. So I don't need to consider the angular part of the metric. So radial light rays, and it's light rays, so ds square is 0, which means that in this case I can simply write c dt equals a as a function of t times dr. So this is what I can use from the metric directly. And how do I consider the Hubble's observation? Now what I am drawing here is not a space-time diagram but a schematic diagram. So which I label here because if I call it a space-time diagram, there will be some mistake to call it a space-time diagram, but I don't have enough time in the course left to explain all to you. What I'm drawing in the x-axis is r, which is this radial coordinate, and y-axis is c times time. And we consider the two galaxies, and in this case we consider them to be at the same r. They remain as the same r as the time progresses. So these are their trajectories or wall lines. I write stationary, which means that their r coordinate doesn't change. So one of them can be us, say call it r equals to r1, the other is r equals to r2. So as the universe is homogeneous and isotropic, you can choose the origin wherever you want. I can choose the origin at r equals to r1. Okay, now what happens? So from r equals to r1, or okay, so I can choose the observers here. That will be easier, as you will see. And this is the emission. The light is being emitted from that galaxy. So this is the spectral line we were talking about earlier. So this light has emitted, so it has reached here. And a spectral line which looks, I'm just drawing the spectral line here. So which basically you can think of an oscillation. Oscillation will look like this because with time it will oscillate. If you think of a pendulum, for example, it will oscillate in space. So that is one of the at one of the crest you have sent this, and in the other crest which comes here, you send the other light rays. So if I call this time, so let me now draw this equitime axis here. So this, I call this time as t emitted, and this as now t emitted plus delta t emitted, and you can see the way I have drawn the light rays, drawn the oscillations. Delta t emitted is essentially the time period of the oscillation. So this is t observed, and this I will call t observed plus delta t observed, as we expect, as we know from the observation done by Hubble, that the time period of the observed rays is different than the time period of the emitted ray. So delta TE and delta TO is expected to be different. Okay, so let's see what we are up to. So we are looking at this expression now, and I'll try to figure out what is dr. Well, dr is always r2 minus r1, because as I said that we have not considered any motion of the galaxy. So essentially it is not a Doppler effect that we are talking about earlier, as Hubble had explained it. So that r2 minus r1, and let us divide it by c just for sanity. This is integral of r1 to r2 dr by c, and it should be equals to, just from this relation, and we are, so I have two light rays. So I am talking about the first light ray first, and that is emitted at t emitted and observed at t observed. So this should be this integral. This for the first light ray. For the second light ray, it is still r2 minus r1 by c, because the galaxies, as we have assumed, they doesn't move. But the time integral is now different. The time integral limits will now be t emitted plus delta t emitted to t observed plus delta t observed. So if you want to have a count of that in this diagram, so t emitted plus delta t emitted to t observed plus delta t observed is this time. What we will do is, we'll write this time as a summation of here to here, then there to there, and I have to subtract away this much. So that is, very simple to see. If I do that, I will get back this time interval. So which means I can write this integral as, the first one is Te to T observed, T emitted to T observed, dt by AT. The second one is T emitted T observed to T observed plus delta T observed, and obviously the integrand is same and so is the measure. And then I have to subtract this, which is, so this will be T emitted to okay. So I have these two equations and the left hand side of these equations are same, so I can equate them. And if I equate them, you realize that this term is common in both, so that will go away. So what I will be left with is a simple to see that T observed to T observed plus delta T observed dt by A as a function of T is same as T emitted to T emitted plus delta T emitted dt by AT. And you can imagine that in this small time delta T O or delta TE, this integral can be just considered to be, I can take out the entire integrand, AT doesn't change much. So this essentially means that delta T observed by A at T observed is delta T emitted by A at T emitted. Okay. Now, see, A as a function of T is just a function. And remember that I have to choose the length scale for R. So I can choose the length scale such that whenever I measure the distance between two galaxies today, I call that to be the distance dr. At a different time other than today, this entire distance given by these two quantities will be different, but dr will remain same, which means at present I am choosing A to be 1, and that's a customary choice. So we choose A at T0. T0 is also, it's not 0, it's for us is observed, but is the present time, equals to 1, which is at present essentially. So then I find that delta T observed, which is the time period of the emission observed, is the time period of the emission as it was emitted by the scale factor at the time when the radiation was emitted. And if that is a time period, it will not be much difficult for you to figure out that the wavelength of the radiation will also follow this. And as Hubble was given things in terms of the redshift then, which is defined by lambda observed minus lambda emitted by lambda emitted, and it's called Z in cosmology, I think also in spectroscopy. What this is that it's just 1 by A minus 1. So you find a very useful and famous relation, which is A equals 1 by 1 plus Z. So at present, A equals to 1, the redshift is 0. At past, as Hubble observed, Z greater than 1, so A must be less than 1. And that is what you mean by the expanding universe, because as the time progresses, then at past A was smaller, at present it is more, which means with time the measured size of the universe increases. Now if you look at this expression, So we have A as a function of t times dr. This is giving you the length for anything. And as we said, that in this way of seeing, as the universe progresses in time, r2 minus r1 doesn't change. So this distance r2 minus r1, or this distance which is integral of dr, this I can write as at. This distance between any 2 points, I will write this as dc, which is called the co-moving distance. On the other hand, the entire thing, which is a times d, is called the proper distance, because this is the distance from an observation like Hubble did, is what we will infer. So this is called proper distance. As opposed to a co-moving distance, which is something doesn't change. If the galaxies itself doesn't move, so in this case we consider that galaxies are just staying still. Still, just because there is a scale factor, we saw that there will be a redshift, which is what Hubble has observed. Okay, so what Hubble has observed is dp. Let me just write this expression down over here again. And you can see that dp will be a function of time, obviously. So if I take a derivative of this expression, you will see why we are doing this. It will be clear shortly. I can call this a velocity, which will be essentially a dot. And I forcefully divide it by a, then I get a times dc, which I can write as a dot by a, and a times dc is again nothing but dp, the proper distance. So you get the fact that the redshift, so this was Hubble's conclusion, is that the redshift is this apparent velocity, which we call the proper velocity, divided by c, and that is equals this quantity called h naught times dp by c. This was the Hubble's parameter. This is essentially the value of this quantity a dot by a, the derivative of the scale factor with respect to time divided by the scale factor at present. Okay. And that explains why Hubble saw the redshift. And the Hubble's law, now I have written in terms of a parameter in the Flrw metric. We are talking about the expanding universe model, and let me first summarize what we have known so far. So we started with Hubble's observation, and to summarize it, at least what we have inferred is, if we look at different galaxies, calculate their velocities or estimate their velocities from the redshift of the spectral lines, that he found equals to the or proportional to the distance to those galaxies. This h he called as the Hubble's constant, and probably I wrote it last time also, but today I have to do it explicitly. I call this Hubble constant, but that zero over at the uh, the at the zero at the base of the h essentially describes that it is the value of the Hubble constant at present. And we'll come back to that today, why we call it Hubble constant at present. To understand this observation, we evoke the idea of what we call the cosmological principle. And it's very simple. It essentially tells you that we are not at a very special point in the universe. It tells you that as a whole, the universe is homogeneous and isotropic. So, with these two key ideas, we came about a particular expanding universe model. And I am saying that we came about an expanding universe model just because it is not the only model that could explain the Hubble's law. But it eventually became the model which explains more observations to follow, which we'll discuss later. But that's why we are discussing this model. We are not discussing other models of the universe which were there and were legitimate models to explain Hubble's observation, but probably are not so good in explaining all the other observations that you have done so far after Hubble's. We can consider that the distance that Hubble is measuring as the proper distance, which is equals to what we call the co-moving distance, which doesn't change but related by a factor at, which we call the scale factor. So let me level this as scale factor. And if you remember that at t equals to t0 and 0 again stands from the present, at is 1. And using this, so let me also level these two. So this is proper distance. Hubble's observation showed that the galaxies have redshifted spectra. Remember that that is what we discussed, which means that Vp is greater than 0. So this Vp is greater than 0. Remember, dp is a distance between two objects which cannot be less than 0. So this implies h naught is greater than 0. So h naught greater than 0, so this is h naught, which means this implies a dot by a greater than 0. And we are talking about present, so the value of a dot by a at t equals to t0 greater than 0. And remember, what is the value of a at t equals to t0? The value of a at t equals to t0 is essentially 1. So this implies a dot is greater than 0. So a dot is the rate of change of a. So Hubble's observation of redshifted spectra eventually through all these things essentially implies that a dot, which is nothing but dA by dt, is greater than 0, means a increases. If a increases with time, what happens to dp? Well, dp, if I write as a function of time, is nothing but a as a function of time times the constant distance, co-moving distance. So dp also increases with time. which means what we will always see, that we will always see the galaxies are going apart. And that is what I mean by the expanding universe model. Make no mistake here, the universe is, so far we know, as the spatial part of the universe is infinite. So the spatial extent of the universe is increasing. If you have that notion, when I say you have expanding universe, that is essentially wrong. Because when I say an infinite universe is expanding, it cannot expand into something else. What all we mean by the expanding universe is that when you look at the galaxies or every other object in the universe, which are sufficiently large apart, if you look at me from where you are, you will not see me going apart if I am sitting here. But if you look at the galaxies, which are relatively far away from us, and you will see that they are going apart. That's what the expanding universe model means. And when I say they are going apart, it also means that their co-moving distance is not changing. The co-moving distance, remember, with our definition of co-moving distance, remains the co-moving distance. So this is always, I'm sorry, this is not what I meant. This is always remains the same. This is what is making the universe, making the nearby galaxies going apart, the scale factor. And when I say that they are going apart, I mean that their proper distance to us is increasing. And when I now consider expanding universe model, again, there existed two models, two particular models of the expanding universe, which could explain all these things. And let me just list these two models here, and we will again discuss only one of them. One is called the Big Bang model. And every other people have a complete misconception about what this model is. So I have to be careful here. This model essentially is a model where it says that the matter density, and when I say matter, it can be ordinary matter, it can be dark matter, it can be radiation, it can be many other things. So everything combined. This model is the model where matter density changes with time. This is the definition of the Big Bang model. And remember, and if you look at the definition, there is no mention about any event called Big Bang in this definition. It just says that the matter density changes with time. We'll see today explicitly what particular way does the matter density change with time. Okay, so that is one of the models. What is the other model? The other model is called the steady state model. And it is simply a model, well, a class of model where the matter density does not change with time. Let me just give you a little understanding of what these two models are saying. So remember, both are expanding universe models. In the steady state model, the universe do expand. The expansion of the universe is an observational fact. You cannot deny it. It does expand in the steady state model, but it's a model where the matter density doesn't change with time. Let us consider the meaning of these two models first. Remember that in the expanding universe model, we have this thing that the proper distance increases, right? The proper distance increases in both of these models. So, which means I consider a region in the universe. So, this is a region, hypothetical region in the universe. This is not the entire universe. The entire universe is infinite. I cannot draw it in a given place, given finite place. So this is a region in the universe, and this has a co-moving scale of dc, which means it has a co-moving volume of dc cube. Okay. Inside this, say there are galaxies, n number of galaxies, so ng number of galaxies. Each galaxy has a mass mg. Okay. So what is the total mass inside? If I write it with capital M, it is nothing but mg times ng. I draw this distinction between the two models with this dotted line. Right, so you have this mass, you have this co-moving volume. So at time t1, proper density, let us calculate the proper density. You see, for the co-moving volume, nothing happens to the this co-moving volume as the universe expands. As we have said, that the co-moving distance is always remains the same. So nothing happened to the co-moving volume as the universe expands, which means at a later stage, what will happen to the proper volume? Okay, so at a time t1, what happens to the proper volume compared to this co-moving volume? Well, the proper volume will be just a at t1 times dc entire thing whole cube, because that is how we go from the proper distance to the co-moving distance. So the co-moving volume corresponds to this, sorry, the proper volume corresponds to this co-moving volume is at1 times dc cube. So the proper density will be m by at1 cube times dc cube, and this is the proper density at t1. And you see immediately that at t2, the proper density at a different time t2 is nothing but m by a t2 cube dc cube. So you see that, so this is the density which we call the matter density or the mass density. I write just, so whenever I will call about density, I will talk about the proper density only. So this is a function of t1 or function of t, which goes as 1 by at cube. Or I can also write it as a function of a, then it is easier to understand what it is. It's just 1 by a cube. So that's what I mean by the fact that in this type of expanding universe model, the Big Bang model of the expanding universe, the density changes with time. So So that's how we defined the Big Bang model, where the matter density changes with time. It has to happen because for all expanding universe model, the relation between the proper density and the comoving density has to be this. And if you consider a comoving volume of size dc, then this will happen for if your matter density, this will happen. If the what is the assumption behind this? The assumption behind this is, of course, that we took the same mass in the two cases at the two times t1 and t2. We assume that the mass inside this comoving volume, doesn't change as the time changes. And that's essentially what is relaxed in the other model of the expanding universe, steady state model. So there they says that the mass or matter is created in the universe as it expands, and this keeps the density fixed. Okay, so I will not go into the further detail uh, of the steady state model, because also the fact that it is more complicated than the Big Bang model, and it's not the model which is considered to be the model of the universe, expanding universe today, but that is what it is. So let us go into the discussion of the Big Bang model today. Okay, we have the Flrw metric, and we still say that there is one parameter which is not determined, one function which is not determined, and this will depend now on the energy momentum tensor. So I need to write down now Einstein's equation, which, if you remember, was simply g alpha beta minus, now I will include this term which is the cosmological constant term. What you have to do, you have to put in this, the metric in the Flrw metric in the left hand side, and the right hand side, the energy momentum tensor is, you have to assume something, and we assume this of a perfect fluid, the energy momentum tensor of a perfect fluid. And this energy momentum tensor of a perfect fluid, which we have written earlier, can be written as a diagonal metric with rho c squared and then the pressure terms. And as you remember that the Bianchi identity in terms of the energy momentum tensor is T alpha beta equals 0, and that if I use here, I will get this, will give me, and this is all that you should be able to do. So I am not doing all the mathematics here, I'm just writing down the solutions. This will give you rho dot equals minus 3 rho plus p and a dot by a. This turns out to be, this expression turns out to be the expression, the essentially the first law of thermodynamics, the expression that you will get because of the first law of thermodynamics. I leave it for you to think about it. Now, this expression itself does not give you the full thing. You also need one more thing, which is the relation between P and rho, and that one calls the equation of state. The equation of state in the context of cosmology is considered to be very simple. It's considered that the pressure is related to the density this way, where omega is called the equation of state, which is the same as what is written here, parameter. And it will differ for different type of objects. For dust, which we discussed earlier when we discussed the energy momentum tensor, omega is 1. Omega is 0 for dust. For radiation, omega is 1. And what you can do is, if instead of writing this expression, the Einstein equation this way, if I would have kept this term in the right hand side and then forcefully called lambda as a part of the energy momentum tensor, then and assume that that energy momentum tensor also has this type of components, you can try to do it. You will see in that case it is easy to figure out what is the relation between P and rho, because we actually know what are the components of this energy momentum tensor, which comes just because of lambda. And you will see that lambda, which is also called the cosmological constant, this is just writing forcefully, keeping it in the same footing. So this will come out to be -1. Okay. So now, if I use this in this expression, let's see what will happen. So I will get rho dot. You see that P will just becomes omega rho. So I can take rho common outside and take in the left hand side. So I'll just get -3 into 1 plus omega A dot by A. And immediately you can now solve it. Omega is just a constant. You can immediately solve it, and you will get rho is rho 0. I will tell you what is rho 0. What rho 0 is, minus 1 plus omega into 3. 3 into 1 plus omega. I should write it properly. It is 3 into 1 plus omega. So for dust, rho is rho 0 a to the minus 3. Rho 0, you can imagine now what it is. At present, a equals to 1. So rho 0 is the value of the density at present. I'm sorry, for radiation, this is supposed to be 1/3. So radiation omega is 1/3. So 1/3 plus 1 is 4/3 by -3. So rho will be rho 0 to the minus a minus 4. And for cosmological constant, it will be just a constant. So total density of the universe, I can now write as rho as a function of a is rho. I write gamma naught, which is gamma is for the radiation, a to the minus 4 plus rho matter naught. Matter is for matter, of course, plus rho lambda naught. This is the total density of the universe. Considering lambda to be a part of the density, and that drill I have already told you. So that's it. Now, if that is the case, then I can now know everything about the right hand side of the Einstein equation, and even I have clubbed that lambda into the right hand side. G alpha beta, as I said, I can calculate directly from the Flrw metric. So now we'll get the solution or the equation to solve the scale factor AT. So this is called the Friedmann solution. The Friedmann solution is A dot by A whole square. This is obviously a function of time, is 8 by G by 3 rho as a function of A. And the rho as a function of A is written in the previous line. And that's it. So that is now what I have to do is that I have to put rho as a function of A. And if I know the value of the parameters, rho omega naught, rho matter naught, rho lambda naught, etc. So let me remind you. So this is radiation. This is matter or dust. And this is cosmological constant. So if I know these values, then I know how A behaves as a function of time. Remember, A dot by A is nothing but the Hubble's constant h, and A dot by A at t equals t0 is what we defined as h naught. And let us also define rho at t equals t0. We'll call this rho c0. So if I used these, so I get from here A dot square by A square is nothing but h naught square is equals 8 by G by 3 rho C naught. This is called the critical density of the universe. So what I get? So I can write now 8 pi G by 3 as h naught square by rho C naught, just from changing this a little bit here and there, which means that I get A dot square by A square equals h naught square times rho by rho C naught. I can write h of A square is h naught square times, this is the entire rho, so that has rho gamma naught, and remember I had rho critical naught in the denominator, times a to the minus 4 plus rho matter naught by rho critical naught in the denominator, a to the minus 3 plus rho lambda naught by rho critical naught in the denominator. Okay, and now this gets names. So this quantity is called, these are called omega parameters. So this quantity is called omega gamma at present. You can see it is dimensionless. It's the ratio of two densities. Similarly, this quantity is called rho matter naught, and this quantity is called, gamma, omega matter naught and omega lambda naught. So these are called the omega parameters, and these are very important parameters in the present understanding of cosmology. So we have got 4 parameters which are very important, h naught and 3 omegas. And let's see that are they 4 parameters or not. That we should be clear right now. See what happens at present again. So this equation, let me first write it in terms of the omegas. This equation is something that should be in your mind all the time, because this is one of the fundamental equations in cosmology. Remember that A is 1 by 1 plus Z. So with some abuse of mathematics, I can write the same thing as h square as a function of Z equals h naught square omega gamma naught 1 plus Z cube, 4 now, plus right. What happens at A equals to 1, t equals to t0, which corresponds to A equals 1 or Z equals 0? You immediately see that the left hand side becomes h naught square. Here also I have h naught square. So if I write if I divide h naught square by h naught square, I will get 1. And here the z's will be 0. So it will get just the summation of the 3 omegas. That is the case obviously when the universe is flat. So the energy of the universe we chose to be 0. Energy of the part of the universe we looked at, we chose to be 0. So that is only when this will happen. Okay, so this set of equations which is in front of you now are considered to be the most important equations of the standard cosmology. Let me keep here the other definitions also. Okay. Fine. So I will request you, whatever is there in this particular slide right now, to have a very, very good idea about these equations. Once you have seen these, you should never forget. You should never forget the meaning of each and every lines, every points in these equations. So that's the basic of the present cosmology. Let me also give you the values of these parameters. I'll ask you to look at the value of this. This is very small. We'll actually calculate that. This is about 0.3, and as I said, the first one is very small, so this has to be around 0.7. Okay, so these are the most important equations of the standard cosmology. Fine. So we have looked at these most important equations of standard cosmology, and let us now try to understand the solution of these equations. How does A varies as a function of t given these things? So remember that what is not written over here is the fact that h of A is A dot by A, and that's what we will use to see or to foresee the solution of these.